This is the basic formulae for calculating the number of samples you need per group. So you'll see these things that I described are all in the formulae. You've got the delta, which is the size of a difference to detect, the minimal effect that's of interest to you, standard deviation. Alpha and beta come into these Z statistics, which I'll explain in a minute. Basically, the Z statistics are points on what's known as a normal distribution required to give the required power and significance. So that I'll show those in a second. They're not really difficult. They're actually fixed values you can just put in, so it's not really making the formulae that much more difficult. This formula is most suitable when the data are normally distributed. It's for continuous data. Obviously, in some situations, you think your data are probably not going to be normally distributed, or you don't know they're going to be normally distributed. And unfortunately, there's no ideal formulae for when you're in that situation. So it's probably, even in that situation, it's best to use this formula because it'll turn out to be conservative if you have got non-normal data. If you were to use this formula and the data are non-normal, you're going to get a larger number of animals than you might find that you actually need in practice to get statistical significance, because non-normal data tends to have quite a high variability. There might be sort of outlying values or values at the limit of the range of the distribution. So I would still consider using that even if you don't think your data are normal, unless of course you can transform it using a log transformation or something to be more symmetrically or normally distributed. So these Z statistics that went into the formulae, just to give a bit of background as to where they come from the standard normal distribution. This is a plot of the normal distribution, and the Z statistics are determined by the point where the area here is going to be equal to, say, the required power. So you'd want 90% of the area to be in this point to get the Z statistic for 90% power. So, but if beta was 80%, you wanted 80% power, Z would be a little bit lower to denote that. And the same thing for significance. We have to sort of consider, well, I won't go into the details, but basically we have to say 1 minus the significance level over 2. So what we're looking for then is the point on the normal distribution where 97.5% of the area or probability is here. So the Z sort of moves along a bit. We've got a higher value of Z for a 5% significance level. These values are calculated by statistical software, so you don't need to sort of think about using tables as people did in the past. And in fact, you don't need to think that much about it at all, because typically you're dealing with 5% significance, and it's well known that the Z value relating to that is 1.96. That's the value that gets used for 95% confidence intervals as well. And for 80% power and 90% power, the values sort of, you can just take those from what's already known, 0.84 and 1.28. So basically these are the Z values for most situations that need to go into this formulae up here. So you don't need to sort of worry too much about those and thinking about how on earth am I going to find out what the appropriate value of Z is